Can you hear in the back?
Yep.
Okay, so I'm going to talk about the electron. So I'm going to talk about electron diffraction of a 2D crystal, and basically for the electron crystallography, the imaging and diffraction are basically two integrated part of this technique. So for the imaging, what you can get is that basically you get both phase and amplitude from each refraction spot. Because if you call it imaging, you free transform, then you get both phase and amplitude. However, in the imaging case, the phase and the amplitude particularly is modulated basically modified by the contrast transfer function and amplitude function, all these things. And however, in principle, one can determine the structure of a 2D crystal using image only. Because if you can get both amplitude and as well as the phase, you can correct for all this contrast transfer function, and you get both the information. Then you can just do a reverse Fourier transform. You can get a structure. However, practically this is actually quite difficult, because the reason is that if you have we all know that recording imaging to a high resolution is quite difficult, particularly when the image is tilted. If you want to get an atomic resolution, say 3 angstrom or 2.5 angstrom and 2 angstrom structure pure from the imaging is quite challenging. And then I don't know if since this ever been demonstrated to that high resolution using imaging alone. So most cases what you would do is they use imaging and to provide you the phase information, while you use electron diffraction, which gives you the amplitude. Because in the electron diffraction, you provide this amplitude without the modulation of the CTF. And also, it's actually relatively easy to record, and then to correcting the data for diffraction than for the imaging. However, this is the same for the X-ray crystallographer. If you only have the electron diffraction, then you won't be able to determine the structure, simply because in the electron diffraction, you lose all the phase information. You don't have the phase. So unless you can use other methods, such as molecular replacement or other way in which you can get the phase out of for the diffraction, that you cannot really determine the structure by diffraction alone. So that's the limitation of the diffraction. And so this is the yeah, that's basically the outline I'm going to talk about today. Is that a number of things that basically started with the principle of electron diffraction. I'll show a little bit of the formula again. So and also how to set up microscope for correcting diffraction, and also the conditions, and then for how to optimize the condition and the things like that. We'll go through all this one by one. But here, all our discussion is that we assume that you already got very large crystal by crystallization of a membrane protein, a very large crystal, which is suitable, large enough to give diffraction. And also you're able to make perfect grids, and using this perfect carbon film, and which people just talked about how to do that, and using a perfect molybdenum grids. And on this assumption is that you can get diffraction. The question now is how do you get diffraction? So that's what we're going to talk about. So talk about a little bit about the basic principle of how to get the electron diffraction. This is a much more simplified diagram compared to what I just showed you. And basically you have a 2-lens system, and then hopefully assume you get a relatively parallel beam. I know that it's difficult to get a perfect parallel beam. Then you have a specimen here, then you have objective lens. Then in the back focal plane, your beam basically focused it, and then you go spread again, and imaging your specimen, you have an imaging plane. So, and then this is in the microscope that you also have a whole bunch of 3 aperture basically. You have a condenser aperture, C2 aperture here, C2 aperture here, and in the back focal plane you have objective aperture, which you often use for imaging, right? There's another aperture in the lowest pole, which is a selective area aperture, which most people don't use at all. For single particle people, they never use it. For morphic people, they never use it. And the only time you actually need to use this aperture is diffraction. I'm going to show you why you need that. So this is how specimen was hit by the beam and then generate the image here. So this is not only lens in the electron microscope. There are a whole bunch of other lenses after there's a objective lens, which is intermediate lens, projection lens, all these things combined together. So what this part of lens does is that it projects whatever you want to see into your viewing screen or your camera, right? So in the also simplified version of this electron magnetic lens is that you have this is a very old, oversimplified picture of an electromagnetic lens, and you run it through a current into this lens so that this lens can change its focal plane. But basically this lens looks like an optical lens, right? You have a object, you have an image, and you have a focal lens. Now how do you change this focal lens? Is by just changing the lens current. So you can switch the lens current to changing the focal lens of the disease to a different lens current, and then generate a different focal lens, and then so off to change your magnification and all this also. Now in terms of the, look at it here, that's why in the electron diffraction it's so simple to switch between the image mode and the diffraction mode. And in early time, in the very first generation of microscope, it is only able to do the electron imaging. And at that time, the diffractometer and the imaging, they are two separate machines. And until the things get combined together, actually you can do these things easily. The thing is that when you change in this part of combination, this part of projection lens and the video lens, all these things, what you do in the normal imaging mode is that you conjugate your back imaging plane to your viewing screen. So in this case, what you see on your imaging viewing screen is everything on the back imaging plane. So basically the image of your specimen. So this is a sort of like image of a specimen. It's not a 2D crystal, but this is just demonstrate how the image is converted from this back imaging plane to the viewing screen. So then what you can do if you want to do the diffraction is that if you switch all this lens current, right, change the combination basically by pushing a button called diffraction, and then you switch this whole thing, make that what happens is that it make this back focal plane conjugate to the viewing screen. So what you're seeing actually here and is what actually is effectively like you putting a detector at this level. This is just similar as in the X-ray diffraction, that you put your detector right in the focal plane that you record the diffraction. But here it's possible a whole bunch of this lens that is recorded on your image. So this is a diffraction pattern. And then so that's basically by pushing that button, you change all the configuration of the microscope so that you can simply record the scenes here. Now also you have to think about this is actually different from from X-ray diffraction. Because in X-ray diffraction, you simply put your detector actually here in this position. Now in the EM, your detector is off the whole this bunch of lenses. It's actually beam goes through all this back imaging plane, and then what you see actually here is already being possible to hold this lens. So this gives us also the why this aperture actually plays a role here. Even it's behind the back focal plane where the diffraction was generated. So this is basically how the in an electron microscope, or how you when you push that button you can record the electron diffraction. Now we also go into a little bit of the formula about describe how you get diffraction, how diffraction is formed. So this is very similar as I did just showed you, that based on this on a weak phase approximation, that in the electron microscope, basically you treat whole thing into two separate steps. The first step is that the interaction between the instant beam, the electron beam, with the specimen. Then the second step is once the beam penetrates the specimen, when they leave the specimen, then that's the time that when the images start forming, and how this propagation of the beam goes through all these lens and then making the back focal plane form the diffraction, and in the back image plane form the image. So if you simplify this one, basically what happens is that you assume that your sample is thin enough. It's very thin that you cannot really see anything in the z direction. So basically, no matter how thick is the sample, you assume this is a two-dimensional plane, right? You don't see anything around the z. And also you assume that your instant beam and then the diffraction is electric scattering, that you do not lose the intensity. And the intensity is the same. The only thing changes is the phase shift. So basically, you can describe like this one, the income beam, exit beam, and then with additional phase. Now, this phase carries the information from your specimen. Now, in a weak phase approximation, which Bob and Dylan both mentioned that you can, after approximation, you can make them look like this way. And then this is how when the beam after came out of specimen, a very simplified version. Then from the back excess plane of the specimen, when they transfer to the propagate to the rest of the part of the microscope, what happens if you look at the back focal plane, it's very simple, just a Fourier transform of the what you have here. And then when it further goes to imaging plane, is another Fourier transform. It's the same as the optical microscope. It's very simple. And if you took the Fourier transform in the look at the back focal plane, this is what you're going to get. So you do a Fourier transform of this thing, and you get a depth function, which is the central beam, plus a Fourier transform of this your potential projection potential of the specimen. And now, of course, here it comes crazy with all this CTF and then this extra phase, and then added to the because of this lens imperfection. So end up that you have this term plus a aperture function, which is because you put an objective aperture there, and then plus a CTF for what is this modulation of the CTF. Now, what you have is that if you look at the back focal plane, what you recorded there in the diffraction is basically a square of this one, right? So this one you can see that this phase actual phase shift is equal 1, and the aperture you don't need to consider because there you don't put aperture. So that you end up with just a Fourier transform of your XF plane without anything of to do with the lens imperfection. Now this Fourier transform basically gives you a structure factor, the square of the structure factor of if you have 2D crystal, right? So what this one tells you that even you have this CTF, all this in there, but in the diffraction plane you don't see all this. So this also means that you cannot actually measure the CTF by diffraction. People ask this question, right? The student asks this question: why, if you measure CTF so complicated, why can't you just do a diffraction and measure it there? But it should show that it doesn't work this way. You can't do that. And of course, you can also go further down from here. You will get an image. If you do another Fourier transform of this term, you can end up with this is how the image looks like in your back imaging plane. And what you actually recorded is this intensity, right? So it's in this term, basically it's your projection potential, but modulated by the CTF, right? So that's why the image you look like is not exactly shows the same as what your potential projection looks like after counter transfer function modulation. That's what you have. So if you do a Fourier transform of this term, you do able to get back to your structure factor together with the phase. However, this is modulated by the counter transfer function. So which means that your phase is free if there is a flipping in the CTF, and then your amplitude is modulated. So compared with diffraction you have there, which is just a structure factor, you will think that it is, if you want to get a more accurate amplitude of your 2D crystal, it's better to get this one from the diffraction rather than from the image. Of course, a lot of time that the images, the crystal is too small, that it's difficult to do the actual diffraction. Therefore, there's no choice. You have to get both from here. But if you do have a choice, if your crystal is large enough to do the diffraction, it is always better to get your amplitude from diffraction than from the image. So this is basically how the image is formed and how diffraction formed and why you need the diffraction. Now the next thing we're going to see that how we're going to set up the microscope and collecting diffraction. And yesterday afternoon we went to a demo. What I did, I wasn't really familiar with the microscope setup, so did not really show very well. And then no people showed actually demonstrate very well this principle how to do that. So basically, you still consider a number of things. You still need to use low dose. You still want to minimize your dose, and for when you set up your microscope to record the diffraction. So for me, and I think for no people are saying that we always use a search mode in the diffraction mode. So you using overfocus diffraction. So this is a image of this is just a calculus crystal I bought from, I don't have a 2D crystal in my lab to actually try this sort of thing. So this is just a calculus crystal, I think probably negative scaling or something. And then, but this is in a search mode, in overfocus search mode. You can see all the crystal, and also you have using very weak beam, you can find your crystal and do the diffraction. Now, to do the diffraction, there are a number of things you need to consider here. Now, one thing is that you want to try to make your beam parallel, and we will mention that later on why it is important as parallel as possible, so your spots can be very sharp. And however, this choice is very small, so you can change your beam size very small and big, any size you want. It's easy to do that, but not all of beam size as a parallel beam. So if you want a parallel beam, your choice is quite limited. Basically, you can do that by changing the condenser aperture, changing the spot size, and then getting the proper size of the beam, but in a roughly quite parallel condition. So this is how you set up your search, your exposure mode. So now the trick is that how to correlate what you actually see in taking diffraction in the exposure mode, and then how with the part which you find you want to take the picture, you know that which crystal you want to shoot the diffraction from this search mode. So the way to do that is that you find an area where there's no crystal destroyed, right? Then you go to your search mode, and you burn a burn mark in your search mode. So this is, you can see that, in your exposure mode. You can see that this burn mark is actually burned in the exposure mode. So this is your beam size, and this is the center, roughly the center of your beam, right? So anything inside this beam will be generating a diffraction, right, contributing to forming diffraction. So you put a burn mark here, so you can put your beam stop somewhere here. And of course, this is a lousy beam stop, and then here you have a much better one. And then you put a beam stop, so then you can move around your specimen. Then you know that anything crystal you put in here, in this position, in the when you push the diffraction button and switch to the exposure mode, your beam will hit this crystal. So that's how you do that. You move another crystal into this area. Then what you do is that, because remember here, your beam is actually very large size, right? And then your crystal is much smaller. And if you have a beam size of this one, you're including many other things included into the diffraction. So you will have a mixture of not only one, from a diffraction not from only one crystal, but from a whole bunch of different things, which generate a lot of mass in your diffraction. So what you do is that you put in an aperture. So this aperture has the size, it was shifted a little bit, but this crystal, right? This aperture has the right size that it selected the exact area you want to generate diffraction. Then you switch to the exposure mode, and then you generate the electron diffraction pattern, and you record them. Of course, this one I don't see any actual spots, but doesn't mean that if you have a good crystal, have a good microscope, a proper setup, you should be able to get a very good diffraction. Now go back to the search mode again, so you can see that this is the beam actually burning, right? And then this is because I put an aperture here, so I will get a diffraction only from this crystal. Actually, I'm recording. So then you go basically cycle through this mode, search, focus, and exposure, and going back and forth, and then just like you're recording your normal image, right? So you ask you that because we actually only mentioned about the two modes, search and exposure, why you need to do the focus. And you sometimes can skip this focusing, but focus is also important. We'll mention it later. So assume that you have assume this is a good, beautiful crystal, 2D crystal like octodopsine, and then following this procedure, so this is what you're going to get. Right? This is the diffraction pattern of octodopsine at 2.5 and a little better than 2.50 dBq using Yoshi's microscope in a liquid heating temperature. Now that's basically a good diffraction pattern. And now what we think is that the next thing we want to talk about is what the things to think about it when you sit in front of a microscope. How do you want to set everything and to record a good electron diffraction pattern? So what is a good electron diffraction pattern? A very good one, a perfect one, I wouldn't be able to call perfect, but a very good one should come with very sharp diffraction spots, right, towards the high resolution. You don't want spots very smeared. You want them very sharp. And also you want them not mixed with spots from different crystals. So this makes your data process much simpler. And then also you want a very good, basically very good symmetrical background distribution. So why this is important? Because you have to do the background subtraction. If your background distribution is asymmetrical, then you have after background subtraction, your spots will, your Friedel pair spots will have a very different intensity, which is not good. So you also want to have a basically this is a good geometry, to a good symmetry. Basically, the intensity of the Friedel pair should be equal. So you have a HK spot, and the intensity of this one should be equal to the minus H minus K. So this is the so that's the thing that why you need to get this good background subtraction. So the other thing you also want is that you want spots to be sufficiently apart. This is same as in X-ray crystallography, right? You want spots also be float apart so you can do better integration. And you also want to optimize your exposure time or this sort of thing that to avoid overflow of the central spot, because the central beam is very strong. And usually we put a beam stop here. And but even for the large crystal, that you still, I mean, sometimes you get a problem with overflow. So you want to optimize your exposure time. So these are a number of things that you need to consider. And for each of these things, that you have a solution what actually go together. So for example, how to get a sharp beam, you need a parallel beam, and you need a well-focused diffraction pattern, and you need to use selective area. So we'll go through this one by one. So first of all, you need for getting the sharp spot, you need a good parallel beam. And why is that? Because if you have you need a parallel beam, and you also need a well focus on the diffraction. So in the diffraction, there's not good diffraction focusing, right? What you do that is different from imaging focusing. This one is basically just which plane that is conjugate to your viewing screen. So if you really focus right here, you will get a sharp spot. If you over focus or under focus, you will get a disc rather than a sharp spot. Basically, you're focusing actually imaging either here or here instead of this crossover position. Now, why you also need a parallel beam? Because only when you have, if you have a say converging beam, a rather large angle or diverging beam, either way. But what it ends up is that if you have a converging beam, which means that you have actually many parallel beam on different orientation, right, over a angle. And each of these parallel beam will focus on a different point. And what you end up is that instead of having a sharp spot, you will have a disc. Which is sometimes, it's not a perfect, but if the disc is not too big, it's not a big problem. But the problem is that if you focus, if your angle is too large, then this disc will become too big, and you actually start to see features in this disc that is no longer really give you an intensity, an integrated intensity of this refraction. Then you have a problem. So that's why that when you set up your beam, say also your crystal is only this big, but your beam is this big. You cannot just say I focus my beam to make the beam at the size of my crystal, and then so that I don't use aperture, and then I can just generate a diffraction. So that case, sometimes you do get what we call a convergent beam electron diffraction, which is you see a disc rather than a sharp spot. So this is another thing that why you need a parallel beam and well-focused one to get a sharp spot. Now, what happens is you have a large beam, and this is your beam size. It's parallel to give you a sharp spot. But my crystal is only this big, right? It's tiny, much smaller than my beam size. And then what ends up is that I have in the back focal plane here is basically here is a diffraction pattern generated by everything inside the beam, right? So what you're going to do with this case is that then you can using the selected area aperture, which is the lowest aperture, which is in this position. What you can see is that also the diffraction pattern generated here is from everything inside this beam. But all this thing goes through the remaining length until it hits the viewing screen, right? So if you put an aperture here, say selected only this crystal, your crystal. Now this convert back here is that what happens is that this aperture only allows also beam is hitting this area, but only the beam hit the crystal is allowed to pause this aperture and hit your back focal plane, the back viewing screen. So in this way, then you are in your diffraction pattern you actually record it is only from this small crystal when you're using a selected area aperture. Even the beam is hitting a much larger area. So this is very different from X-ray crystallography. In the X-ray, you mount a crystal, which is a single crystal at this position. You hit the beam and record everything here. Now we cannot do that, but this also gives us an advantage that even we have a mixture of many different crystals, even you have overlap, but you can select a small area which has given you a single crystal and using this selected area aperture and by the end recording a good diffraction. So then the other thing is that you want a good symmetrical background. Now this is an electron diffraction pattern without doing the background subtraction. You can see that you have a much stronger intensity, background intensity from here all the way goes to the edge. Right? If you look at the background, this is a symmetrical background. Assume the symmetrically distributed background. This was subtracted from determined from the previous diffraction. Now this is not insufficient to describe the whole background. What you actually have is also some sort of a symmetrical background. And in this case, this is a very good diffraction pattern. Therefore, this one background is actually quite symmetrical. So your alpha-Riedel will give a very good alpha-Riedel value. However, what actually happened with this one, that you can actually get in a very bad background. So, for example, if your image, you set up your diffraction, but your specimen or your image is not in focus, right? In the image mode, it's not in focus. If you say 10 micron away from focus, what you end up with is that you will have a very asymmetrical background there. And then when you do a background subtraction, you will get a very uneven distribution. Then your alpha-Riedel of such diffraction spots will be very bad. And this is particularly severe if you have a tilted specimen. I mean, it's not say particularly you have to be very perfectly have a good focus. I mean, 1 micron or something off, it doesn't matter. So that's why when you do a untilted specimen, it's quite simple. You focus once, they can take all correcting diffraction pattern off the entire day, and then you don't have a problem. But if you have a tilted specimen, particularly like say 60, 70 degree tilted one, and then from one area of the specimen to also another area of the specimen, the heights change dramatically, change a lot. So your focus also in the image changes a lot. So if you do not correct for your objective lens current to make your lens image right in the focus, what you end up is that you have a very symmetrical background. And then when you do a background subtraction, even you have a very good diffraction pattern, diffraction very high, but after background subtraction, then your alpha-Riedel is very bad. So it means that your scores from plus and minus same index is very different. So in this case, that you can see that after background subtraction, the spots actually are very symmetrical. You can see the bright corresponding to bright. So this is very good. And then what happened in the tilted one, this is a 60 degree tilted diffraction pattern. You can see that this is also a very good one, and then we're focused in the images. So if you look at this, the same pattern, just to scale them in a different way, you can see actually there is a background. But this background is also elongated along the tilt axis, but it's still symmetrical. And then you still have a symmetrical background, smooth background, and also another symmetrical background. But this is also quite symmetrical in this way. But if your image is really out of focus, you will get something really weird. I actually don't have example to show you. And so, because those images, when we see this like this, we never process them. So that's why this focusing is actually important. So that's why a number of things you need to consider when you do the diffraction. So the other things to think about it is that camera lens is one thing which is important to think about what camera lens you use. So the camera lens, what I usually choose is that depends on this, really depends on the detector. You use a film, or you use a CCD camera, you have a 2K camera, or 4K camera, or 8K camera, or 10K camera, depending on the size of the camera. You can choose your diffraction camera lens. The point is that you try to get your highest diffraction achievable to really far away, so you can maximize the distance between the spots. So in this way, it gives you much better background subtraction. So, but this is the limiting factor is actually the size of the camera. So it depends on what kind of camera. If you use a 2K camera, then you cannot really use in a very large camera lens. So the other thing is that the dose. Of course, you need to minimize your dose to reduce your radiation damage. Minimize dose means that you minimize the dose used for searching and other things, not say for recording diffraction, right? Now you're also using a beam stop to block the central directed beam, so to prevent overflow. All the cameras is overflow problem, so that if you have too strong overflow in the center, it actually can ruin your diffraction pattern. Now, the other thing is that people often ask what exposure time, and this part depends on what aperture you select, how big is the crystal, and then things like that. So the thing is this: if you have a very small crystal, which is very well ordered, right? You want to use as long exposure as possible to get the highest diffraction spots. However, in this way, your total amount of dose used actually also probably overdose. And however, you still get a high diffraction spots, but your temperature factor will be probably not very good, which means that because imagine that if you use longer exposure and then overdose them, the high resolution spots will start to disappear after a while, but your low resolution intensity is still there, right? And cumulatively, this Wilson plot will become a very deep slope, but you still get a high diffraction spot. But on the other hand, if you have a very large crystal, then you have to use you can use a very large selective aperture. The many beam can pass through. Then you have a problem of overflow your central beam, because if you cannot expose that same long, you have to reduce the exposure time to prevent the overflow. So I always thought that it would be nice to have a beam stop of different size, depends on your crystal. You have a large crystal, you can use a large beam stop, and then you still use the same long exposure time to really get a high resolution diffraction. But if you have a small crystal, use a small beam stop. I also to use sort of two beam stops, so the different size you can choose, right? But it was never actually in this way.
So one thing we found with the big of 1.0 crystals is that it's actually still better to just expose small areas, right? Because the larger the area you expose, the bigger is your chance that you get.
Yes,
crystals.
you also get an imperfect crystal. Then your spots may not be as sharp as you use small aperture. So in that case, you have to either waste some of the crystal not being recorded, or you can really reduce your size and use small aperture, make the size of the beam really similar to your aperture, so you can take a multiple shot. Right? So yeah, but that's another way. So that's it for this. And then after that is basically what you do is you do you process the data. And the process data is rather simple. I think that I never used this in 3DX. You package it, it's very good and much easy to use. So the example I show you here is actually still use a old package based on MRC. And
5 minutes.
okay, I will get that. So using the MRC package, and then was the interface that I was in almost like 10 years ago using Hiroshi's lab. So do you have a diffraction pattern, and then you can determine your lattice and your tilt angle and tilt axis, and then you mark out all this area between the spots to determine your background. And then you subtract your background, you get your background subtracted diffraction pattern. Then you integrate all the spots over all the diffractions, calculate the integrated intensity, and then you also assess the quality of them, say how good is off-redale and how many strong spots with high resolution, etc., etc. So in this case, that we have the things that which actually in this example that we have a diffraction to a little better than 2.5 angstrom. In alpha 4.0, we get about 1.9 angstrom. And then, of course, with one diffraction is not sufficient to give you the entire 3D reconstruction. So what you end up is you need to take diffraction from different angles. Right? Each angle is a section cutting through this center, and then cutting through all this refraction ball into the space, give you a diffraction pattern. Then you can merge all of them together. And then basically, this is often people call it like a 3D reconstruction in reciprocal space. And basically, so this is a, for example, this is a, we have showed you a 0 degree. So this is a 45-degree chill image, a diffraction pattern. And you have a 60 degree, and then you have a 70 degree. Otherwise, all these things together, you have a merged lattice line, and of different lattice lines. And you can see that they all extended to a reasonably good high resolution. And then from there, you can calculate your structure. Now also, back to the question that that I was sort of supposed to mention a little bit about what CCD or film to use. And then traditionally, I mean, 10 years ago, more than 10 years ago, 20 years ago, we used film. We always use film. There's no CCD. And then now, once the CCD come along, the CCD is, in my for diffraction, is absolutely better than film. There's no debate, no question to ask. There's no doubt about it. The reason is that this is imaging is very different. Diffraction is very different from imaging. In the imaging, you consider MTF, point square function, is very important. But for diffraction, you really worry about the dynamic range. And the film has a much worse dynamic range compared with a CCD camera. 20 years ago, when we recorded diffraction pattern, to gain the dynamic range, you have to take a serial exposure on many diffraction patterns. Some overexposure, some lower, then you merge them together to get a completely intensity distribution. And then with CCD camera, you don't need to do this. So you really need to, there's no point to, I mean, it's absolutely, I mean, now there's no point to use film for diffraction. But another thing that, which I remember when I was in Thompson, we saw the trials that are using imaging plates for diffraction.
Yeah, we did.
I don't know how good is the results, whether it's better or worse than probably. So imaging plates.
Just very quickly, so the imaging plates are kind of interesting because you don't need a beam stop, so we thought we could actually measure everything from the very low to the very high resolution. Has an even better dynamic range than CCD camera, and we thought we would have a larger imaging area. So we didn't use the best imaging plates scanner, and we didn't use the best CCD camera. But what we found was basically, even though we don't need the beam stop, we can't measure the low resolution spots just simply because the inelastic scattering background is so anisotropic that we can't correct for it. So whether you have a beam stop or not, you can't measure the low resolution spots. Then a problem with imaging plates is that the information dissipates. And so we actually kept the imaging plates in the microscope and scanned them the next day. But that wasn't a problem, that was actually still very good. But then when you will process data, both on CCD camera and imaging plates, the statistics in the end is pretty much the same. So you don't gain very much using imaging plates. Well, you actually have to weed them out, and you have only 56 plates in the microscope. So with the CCD camera, it's much more straightforward to see what you get. And then also the area of the imaging plate doesn't really improve much over a 2K CCD camera. So if you can use a 4K CCD camera, you're actually pretty much better off than using imaging plates. So I would not recommend imaging plates at this point.
So probably now, if it was an 8K camera, we probably even prefer don't need to use that one. And like Yoshi said, we use 8K camera for diffraction. So that's the last thing I want to mention. That after, so I mentioned earlier that you have to, in diffraction alone, you cannot generate phase information. But once you have up to this step, once you have this lattice line, you pretty much basically go into the position that as X-ray crystallographer. While everything else from this point on is the same as X-ray crystallography, pretty much the same. And then, so of course, if you can phase the diffraction using either molecular replacement or any other method, you can phase them, then you can solve the structure. So in this particular Robson case, given the pH than the structure we had before, it was using a molecular replacement to get a structure about 2.5 angstrom. So that's basically all I want to talk today about diffraction.